Hello, friends. It's Ben again. This is a recording about the idea of partial derivatives. This is my second attempt. I'm having problems with wireless connections. So let's see. I'm just checking something real quick here. All right. Let's see if this works this time. So the notion that we've got for our partial derivatives is a lot like the derivatives you did in Calc 1. But we've got an extra variable going on here. And yes, this time it worked. All right. So partial derivatives, we're going to be dealing with something where you have your z variable being set to some function of x and y. You could be using any variables you want to. It doesn't have to be x and y, but that's going to be what I'll write for these examples. We're going to write f sub x to mean the derivative with respect to x, but we could also be writing the partial symbol there, okay? Notice that that's kind of a curly D. In a later section, it will actually be something where we distinguish between the various derivatives we might be thinking about. So keep in mind it should be a curly D to show that it is a partial derivative. But then on the other hand, I need for you to pay super close attention to this right here. If you write f prime, you're wrong. There is no f prime. The reason there's no f prime is that f prime means take the derivative with respect to the one variable we have. Here we have two variables, and hypothetically we can have more than two variables, okay? So f prime is meaningless. If you write it down, I will take off for it. That sounds like I'm being mean, but it might be that I've had the same mistake come up for 28 years of teaching. So there is no f prime, all right? So in any case, though, we're going to be talking about an f sub x or an f sub y, more at a time. Here's our definition for f sub x, and we would be doing exactly the same sort of thing for f sub y. When you did this in Calc 1, they would have had exactly the same definition going on, except it didn't mention y, because there wasn't a y. So all you really have to remember for this is that the y is a constant while the x is changing, all right? I lied. There's another thing you have to remember. If I ask you to do the derivative using the definition and you don't use this definition, then you don't get credit, okay? I realize it's much easier to use the rules, but I have this point that definitions are important, and so I need for you to just go ahead and use the definition for the one or two possible examples that I'll ask you to do, okay? That really sounds whiny of me, and I should stop it. So the short of this is that we're treating y to be a constant, and we're allowing x to change. What we end up getting out of this is the slope of a tangent line, but it's a tangent line that is inside of a cross section. So I have not engaged a professional artist to draw my picture here, but you can see that we have this function of x and y for our z, and as you draw the plane y equals some value y sub naught, that plane can cut across your function there, and in the place that it cuts across, you will have a curve just like what you were used to in Calc 1. And you can talk about the slope of the tangent line to the curve just like you did in Calc 1. The difference, though, is that we can change which cross section we're in, and that may affect what the final answer is. But really, when you do these, it's all about the algebra. All right. So let's look at my first example here. So partial derivatives example 1. So we're going to be asked to calculate what f sub x and f sub y are using the definition. If it says definition, you have to use the definition. If it doesn't say definition, just differentiate like you're used to. Okay. So our function here is x squared y minus y squared. I tried to make it not be too simple, but not to be too hard either. Okay. So the first bit, of course, is plugging in. All I've done at that step is write down the definition. I didn't write sub-zero or an A or B or something. I just went ahead and left it as an X and a Y, okay? And once you've written that down, the next piece is interpretation. So interpreting this, you have to say everywhere that there was an X, I have to replace it with X plus delta X. The Y's just are Y's. You don't do anything with them. Then in the other piece of it, you're just writing down what the actual function definition is. It doesn't have anything weird done to the X's. So once you've got that, really it's all up to stuff now that you have already mastered. You have to algebra the piece that you already had. We had x plus delta x being squared, so we have to use the binomial theorem. If it said cubed, you'd have to cube it, you know. So we get that, and if you'll notice, I also went ahead and distributed my minus here on the last part. And not distributing your minus is the most common error for people to make, okay? So once I did that, then I went ahead and distributed that y out here. And then I tried to simplify. If you notice, I have an x squared y and an x squared y. I have a minus y squared and I have a plus y squared. So you just cancel them out and you're left with this piece down here that says 2x delta xy plus delta x squared y, okay? Now, something you need to remember when you do this, when you come to this stage of it, everything in the numerator that did not have a factor of delta x or delta y, whatever it is you're dealing with, everything that did not have one of those factors will have canceled. If it didn't, that's not because math is wrong, it's because you dropped a term. Usually it's because you just didn't distribute the minus out. Sounding very negative of me, isn't it? Yeah, but I've frequently had people tell me that math just must be wrong because they couldn't make a mistake. They didn't mean it that way, but you know, that's how it came across. So if you get stuff and you have any terms that don't have a delta x or a delta y, go back and check your algebra. And it's usually something pretty easy, okay? Well, once you get that, then you can factor out one of those delta x's. Notice that you had a delta x squared here, so you're still going to have one left when you come down here. But you factor those delta x's out, and then you can cross them out. Don't try to cancel unless you factor it out first, okay? I know you might be able to keep track of things and never make a mistake with it, but I just find it's better to just be super cautious with what we're doing. All right, once we've got that, then we no longer have a 0 over 0 problem. And when you've got that, because delta x is going to 0, when you multiply it by y, that term just disappears and we end up with 2xy. If the question had not said to use the definition, you would have come in here and said, okay, there's the part with the x, here's the part with the y. The part with the y, we treat y like a constant, so it's just going to go away. And so now I'm taking the derivative of x squared times y, just like if you had 7 times x squared. You'd take the derivative of the x squared and get 2x, and then times the y, okay? Because the y is just a constant as far as x is concerned. But 2x times y, which is what we got down here, so everything is working the way we expect it to. So, all right, then we're going to take a look at doing the partial with respect to y here. And yeah, and so just like before, we're substituting in, it's y plus delta y instead of x plus delta x. But it is slightly more complicated in this because you had to put y plus delta y here where y appeared, and also here where there was a y squared. It's not just one place. It has to be in every place that a y appeared, okay? And then, like before, the second piece is just copying the function down. So then you've got to algebra the heck out of this thing, and we get this kind of a messy bit here, all right? So all I did with the first piece of it was to distribute that x squared across, but then with the second piece of it, I went ahead and multiplied out y plus delta y quantity squared, and then distributed a -1, okay? So once we get it to that stage, we can say this and that cancel. This and that cancel. Everything else doesn't have a corresponding thing to cancel, and fortunately it all has a factor of delta y. So in this stage here, we can see that everything has a factor of the delta y, so we can factor out that delta y and then cancel, all right? And when we do that, this stuff here only has a little bit with the delta y hanging on it, but it still does. But as delta y goes to 0, then delta y is certainly going to go to 0, right? But that means that the piece that remains is x squared minus 2y. And if you look back up at the original function that you were dealing with, x squared y minus y squared, taking its derivative, that's what you would have gotten, okay? So, hang on just a second. I have to pause the recording here, sorry. Okay, I'm back. All right, so let's take a look at another example here where we're using the definition, all right? And here I'm hoping that the iPad decides to behave itself. Can I have it? Yes, yay. All right, so this time we're using the definition again, but we're using it to calculate the derivatives of e to the 2y minus x, all right? I should have named that f of xy there, but I just didn't think to write it. So in taking the derivative on this, it said use the definition. So that means we have to use the definition. So for f sub x, that means that wherever there's an x, we will have to replace it with x plus delta x, okay? Otherwise, it remains unchanged. Remember, y is a constant so far as x is concerned. X is the only one that's allowed to change, all right? So then once you've done that, here all I'm doing is distributing out that minus sign, but remember it's inside of an exponent, okay? Now, the thing that you have to spot though is that if you've got this 2y minus x here and this 2y minus x here, they are both in something that we can factor out. So that means that we end up with an e to the 2y minus x being factored out to the front. When you do that, then you have remaining an e to the minus delta x in the first part, but then it's minus just the 1 because you factored everything out of the second part. All right. Now, the step that I took here may seem unfamiliar. You certainly are used to copying something down like that, but in my next step here, I factored out a minus e to the minus delta x. And you should rightly be saying, what in the heck is going on there? I don't know why you did that. I've got to be honest, it's because I knew the answer, okay? Most of math is knowing or guessing the answer and then showing that you're right, okay? So I knew that in this part here, I needed to have this special limit, e to the delta x minus 1 divided by delta x. In the limit is going to go to 1. Remember how sine x over x goes to 1 as x goes to 0? This is the same sort of thing as that, all right? So I knew I needed to get that there, and I could see here that I didn't have quite the right thing to do it. So if I took that piece here, let me put my pen to a finer detail here. If I took this bit here and just factored out the e to the minus delta x, I would have been left with 1 minus e to the positive delta x, right? And I needed to have that in the opposite order. That's the reason why I went ahead and factored a minus out of it, so that I would have it in the order that I needed it to be in, right? So now I'm going to take that piece off there and put us back to the fat marks. All right. So once I get down here, then I know that letting delta x go to 0, this part here that has no delta x symbol in it doesn't change. So that part's fine. This part here has a delta x symbol in it, and as delta x goes to 0, e to the minus delta x, e to the minus 0, needs to go to 1. That's where this minus 1 comes from. And then finally, this special limit that we've got here as e to the delta x minus 1 over delta x, as delta x goes to 0, that goes to 1, okay? And then we've got all the pieces right here, and we can get that our derivative should be minus e to the 2y minus x. And if you had taken this derivative just by going by the rules, you would have said, treat y like a constant. This has a minus x in it. So when I take the derivative of that for the chain rule, I would get a minus e to the 2y minus x. But it is kind of important for you to see, even without applying the chain rule, you could do that by using the definition, okay? Actually, I have to then make the note for y'all. You're not going to have to use the definition every time, just when the question asks you to. And basically, you have to remember your sine of theta over theta as theta goes to 0. Remember that special limit from Calc 1? You got to remember that. And then the 1 for cosine, you should look it up. And then this one that I've just talked about for the exponential. Those are the 3 special limits that we have to remember, okay? So we're doing f sub y here, and like before, we're just substituting in y plus delta y in the place that the y appears. And then we can see that both pieces are going to have an e to the 2y minus delta x that'll factor out of them. And then we have to just think about what that leaves. Since we had a 2 delta y here, then that's why we have an e to the 2 delta y remaining there. And then since there wasn't anything in this other part of it, then you just have the 1, okay? So looking at that, your initial instinct is probably, aha, that's exactly what Ben said before. We've got an e to the delta y up there in the numerator, so that's going to go to 1. Yeah, almost, okay? So the tricky bit here is that I'm thinking about that I have e to the delta y squared. And I'm also thinking about that I have a 1 squared. So I'm factoring out a difference of squares as we go on that. And when I factor that out and come back down here, come on, there we go. And come back down here, then I've got an e to the delta y plus 1 and an e to the delta y minus 1, okay? Again, I knew what the answer was going to be, so I was taking the steps to get it where I needed it, because I know from having done these before, I need to end up with a 2 down here. And I'm going to make that happen with the e to the delta y plus 1. And I also need a e to the delta y minus 1 over delta y. It has to be exactly that limit, not kinda sorta. It has to be exactly that limit for it to work out, right? So once you see all that, as delta y goes to 0, that has absolutely no effect on the 2y minus x. But the e to the delta y plus 1 goes to 2, and the special limit goes to 1. And then that means that we have left for us the 2 e to the 2y minus x, okay? So if you had done this without using the definition, no, go away, okay. You would have just said the derivative of e to the something is e to that something and gotten this part. And then the chain rule would have told you to take the derivative of your 2y minus x. And since y is a variable and x is a constant, because we're taking a derivative with respect to y, then you would have just gotten the 2y, or the 2 from the 2y, and then the 0 from the x, okay? So again, if it doesn't ask you to do it by the definition, you don't have to do it by the definition. And that's demonstrated by this problem here. So this question just asks us to find all the derivatives of x squared sine of 2y, okay? So with the recollection that we are talking about these two variables here, f sub x means take the derivative with respect to x and pretend y is a constant. This is a variable, but this piece is a constant. So I have 2x times that constant. Because y doesn't change, I don't have to do anything to it. And that's it. That's all there was to that. Let's do the f sub y. So for the f sub y, this part here, the sine of 2y, that is your variable. And so the derivative of a sine is a cosine of the same thing, but that the chain rule told you, take the derivative of what's inside. The derivative of 2y is just 2. And then the constant that was hanging on at the front, I'll just put it in there. And it's nice to tidy things up so that they look kind of nice, right? That's it. That's all there is to it. If it just says take the derivative, you just take the derivative. Same thing going on here. So take the derivatives of e to the xy plus the tangent of x minus y. Well, e to the xy is an exponential, so when I take the derivative with respect to x, I'll get e to the xy. But the chain rule says I have to take the derivative of the xy now with respect to x. So xy, y is a constant, And so you'd have 1 times y, and you just leave it there. Plus, now the derivative of tangent is secant squared, and you leave the same stuff inside, and then the chain rule says take the derivative of that stuff inside with respect to x. 1 minus 0, right? So if you want to tidy up a little bit, you'd say, that's not tidy enough. You'd say y e to the xy plus secant squared of x minus y. And that's all you do, okay? Now, on the other hand, if we're doing g sub y, then we're going to come along here, and for our e to the xy, now we're taking the derivative of xy with respect to y, and we'll get x. Plus, now we're going to do tangent. Derivative of tangent is still secant squared x minus y, but the thing we multiply by is the derivative of x minus y with respect to y this time. So the derivative of x is 0, and the derivative of minus y is minus 1. So tidying up, we'd have x e to the xy minus secant squared x minus y. Boom, done, okay? I say boom, done as though that's super easy. If you're not used to it, you might have to go back and watch that again to see all the details. But once you've done a few of these, you will start just writing the final answer down and formatting it and everything nicely as you go along, because it really is what we did in Calc 1, only with more variables. So, all right, one more example here, and this one is about second partial derivatives. So when we talk about partial derivatives, there is more than one variable. Duh, right? But that means when we talk about the second partials, it's kind of like the second partials in Calc 1, except in Calc 1, you were always doing it with respect to the same variable. Now you have f sub xx, f sub yy, but also f sub xy, okay? So I want us to look at this example here, and we're going to make an important observation, okay? So we're going to tackle this. H sub x, this I think is one we did earlier, isn't it? Well, h sub x is going to be 2x, and we just leave that sign of 2y hanging on there, okay? Now we're going to do h sub xx. So the 2 stays there, the derivative of x is 1, and the sign of 2y goes on at the end. Now, if we were asked to do a third derivative, there wouldn't be any x's left, and we'd just get 0 out of it, okay? But keep in mind what we get as we go along here. Now, if we're asked to do h sub xy, and I gotta be super honest with you, my OCD is coming up on me there. That h, okay, that wasn't that much better, but the first one looked awful, okay? So if we say h sub xy, that means to take h sub x and take the derivative with respect to y. Well, 2x is just a constant that hangs on at the front. And now we take the derivative of the sine, which is going to be the cosine, with the same stuff inside, times, because of the chain rule, the derivative of 2y with respect to y is just 2. So that means our h sub xy we got here ends up being 4x cosine of 2y, okay? So keep track of that. Remember that we did that. All right, now we need to do h sub y. And unfortunately, you know, my memory fails me. I have to look back up at it. The h was x squared sine of 2y, right? So doing that h sub y, the x squared is just a constant factor that's at the front. We take the derivative of the sine, is the cosine, and then we pick up the 2 there from the chain rule. So this would be 2x squared cosine 2y, right? And did I forget? No, I didn't. So now we're going to do h sub yx. We did the derivative with respect to y already. Now we're going to do the derivative with respect to x. And in doing that, notice that the x is the part that we think of as changing. And so we end up with a 4x cosine of 2y. What? Look at that. Look at that. We got the same thing. Amazing. It'll never happen again, will it? No, it happens all the time. So your mixed partials are going to turn out to be the same when you change the order. The only proviso I have to put on there is if you make a pathological example with discontinuous functions and stuff, you can create things where it's not going to be the same. But if your differentiation is taking place using just the regular rules of differentiation, and the functions you've got are not something super weird, your mixed partials are going to be the same thing, right? All right, last one here, h sub yy. So remembering that we're looking at this piece here, and the 2x squared is a constant, so we just leave it hanging out the front. And now we have to take the derivative of the cosine of 2y. Well, the derivative of a cosine is a minus 1 times the sine, the same stuff inside, and then we have to multiply by the 2 because of the chain rule, right? So that means we end up with negative 4x squared sine of 2y, okay? And that's it. So I hope you'll find that the derivatives we're doing here, really, they're not harder than Calc 1. And as a matter of fact, they might be easier because you've had so much practice at them at this point that it's not a big deal. However, when it says use the definition, you have to use the definition. Hopefully your Calc 1 teacher made you do that. Okay, so that shouldn't be a big deal, but it was like a year ago, right? So it may be hard to remember how to do it. Do some practice on it. There'll be one on the homework. There will be one on the test, okay? But it'll be a polynomial. I shouldn't have told, right? Okay, see y'all in class. Except I should turn off the recording.